So now we're going to go through an example of this indexing procedure. And so I have this sample for us to look at. There is 6 peaks and the 2 theta values. So this has already been fitted for you, and it's giving you the peak centers of the first 6 peaks. And it goes up to 136 degrees to theta. So this is part of one of the quiz questions, which is to determine which type of cubic lattice this pattern is, and also calculate its lattice parameter. So if you'd like to try that first before we go through the solution, do so. But we're also going to go through this in a second. And the next part is, assuming this is the pattern of an element, use the table in Colity to try to find what element this is. And to start, we're going to use a X-ray wavelength, so lambda, and that's going to be, our lambda value for this is going to be 1.54, and that's in angstroms. So that's the value we're going to use. So if you want, go ahead and pause this video and try to work this out yourself, and then come back after you've answered those quiz questions. Or if you'd like to just go straight to the solutions, we're going to go through that right now. Okay, so the first step, we have the 2 theta values in degrees, and we're going to calculate the sine squared theta. Usually to start with, I just like to convert this. So 2 theta in radians. And the reason I do this isn't because I like radians. It's because the sine function in most spreadsheets tends to be forced to be radians. And so that's why I'm going to convert it. So it's in degrees, so we want to do pi divided by 180, and that should give us radians. And extend that below. And then I can also go ahead and calculate theta. Just to do so, that is simply this divided by 2. Remember that your experimental data is in 2 theta, not theta, so you have to divide. All right, so the next thing I want to do is now is where I need to calculate the sine squared theta. Pretty simple, but let's go ahead and take the sine of theta, and then we square it. So pretty simple. And I'm going to calculate that for each of these peaks. And it's as simple as that. We've got the sine squared theta. That's the first part of our procedure. The next part is where we have to assume a pattern is simple BCC, FCC, or diamond, right? And then we calculate, or we find the S values from the appendix in Colity. So what I'll do is, we have 6 peaks, so I need to find the first 6. So I'm going to switch over for a second, and we're going to look at the appendix so that you can see where I'm getting these values, and then I'll switch back and we'll continue to fill out this spreadsheet. Okay, let's see if we can find the S values for the different structures. So when I talk about the S values, it's again the sum of squares, this h squared plus k squared plus l squared. So for simple, since there is the 100 type peak for simple cubic, then our first allowable S value is 1. So if it's simple cubic, then peak 1 would have an S value of 1. Since there's a 110, there would be a 2 value, and 3, and 4, and 5, all the way up to 6, right? So the allowable S values for simple cubic are simply 1 through 6. However, if we get to face-centered cubic, you can see there's gaps here. So the first one is actually 111, which has an S value of 3. So our first S value would be 3. Then the second one, which is for 200, would be 4, and so on. And the third one would be 8, and so forth. And we get the first 6. And we would do the same thing for BCC. So the first one is 110, and so that is 2. And then the second one is 200, which is 4, and we would keep getting our S values for that. So I'm going to take these values and transpose them into the spreadsheet. We're back, and I showed you how to get the S values for different parts. So in the procedure, I told you that we have to assume a structure. Well, if we're building a spreadsheet, we can simply just put out the values for all four of the structures. So that's what we're going to do here. So you'll remember that my S values for simple were simply 1, 2, 3, 4, 5, and 6. For BCC, it ends up being 2, 4, 6, 8, 10, and 12. Again, if you're wondering where those come from, take a look at Appendix 9. For FCC, it's 3, 4, 8, 11, 12, 16. And for diamond, it's actually 3, 8, 11, 16, 19, and 24. So those are our S values for this case. And so that is the second part of what we're looking for. So to continue that, we want to calculate, now that we have the sine squared theta and we have the S values, we want to calculate sine squared theta divided by S. So for simple cubic, I'll take my value of sine squared theta, which doesn't change, and I'll divide it by the S values. And if I extend this, it will take my sine squared theta value from here and divide it by these values, right? So you can see that we're doing each peak, we're assuming a value here, and we're using the sine squared theta from up here. Okay. And since we have this spreadsheet, we might as well fill everything out. So why don't I go ahead and do the same thing, assuming that it's BCC, taking the same sine squared theta value up here and dividing it by the S values for BCC. And again, continue this for all the peaks. And the same thing for FCC. And the same thing for diamond. And extend. Okay, so really we've just done all the work for all the cubic systems, and so we don't have to do it sequentially. So we've calculated this, and then our next step, step 3, if you remember from the paper earlier, is to see if the values of this sine squared theta value, sine squared theta over S, are equal to one another or close within experimental error. And what you see is, for simple, they're exactly the same. So that could indicate that that's simple. However, they're also the exact same for BCC. Whereas if you look at the values for FCC, you see that these vary quite a bit. And the same thing for diamond, they vary, particularly the first peak compared to the others are quite a bit different. So what this tells us, based on this, is that this structure is either simple or body standard cubic. And I wanted to show you this example because this can illustrate a very common problem with simple cubic versus BCC, is that they look very similar when we look at these values. We can't tell right now if it's simple or BCC because all of these values are the same. So we can just say either or. And the reason for this is the sequence. For simple cubic, we've got 1, 2, 3, 4, 5, 6. For BCC, we've got 2, 4, 6, 8, 10, 12, right? So this is just multiplied by 2. And so you can see why they're going to look the same. And so the differences don't really start showing up until we get much later in the process in terms of the sequence. So a lot of times you can't tell the difference between BCC and simple with only 6 peaks. So that's a frustrating part. So we know it's one or the other. All right. So now what I want you to do is we've got this, we've got these values. What I've done here is I've rearranged the equation to solve for A, assuming my simple cubic assumption is correct. and assuming my BCC assumption is correct. So these are the lattice parameters A for each of those assumptions. So what I want you to do is take a minute or so, pause the video, and go to table 5 in Colity, the one I have a PDF of, and see if either of these values match up for any elements, simple or BCC, with the respective values, and see what kind of matches we can get with that. And when we come back, I will sort of show you what I've got. So I've switched it over to our Canvas page. This is our module for week 6. And you'll see that in the instructional activities, I've added some reference files for you. And so you have the quadratic form, appendix 9, and then this is crystal structure for the elements. This is that appendix 5 that we want to look at. So I'm going to open this. Might take a second to load. But this is the same that I showed you directly from the book. And so what we want to do is we want to see if there's any simple cubic structures with a lattice parameter of 2.0269 angstroms, or any BCC with a lattice parameter of 2.8665. So the values that we had in the spreadsheet. So what I want to basically do is look through the structures first. So there's FCC, there's hexagonal, there's rhombohedral, BCC, which is going to be useful. And then you keep going, you see cubic. So this is cubic A4. One thing you'll notice if you look over to the side here, this is diamond cubic. So this is the diamond cubic structure if you're talking about cubic A4. So if you keep looking, and we still don't see any simple cubic, if I go over here to the other side, haven't found any simple yet. And here, finally. So right here, polonium is cubic, simple cubic, and you'll notice the temperature is minus 10 degrees. So as it turns out, polonium is the only element that has a simple cubic structure. And the only reason that you might have heard of polonium is because it's radioactive and it's actually been used to poison somebody. So it's a very uncommon element, but it is right there. You can see it, polonium. So we'll also notice if we, let me see if I can zoom in here. Maybe not. There we go. Polonium, and then the lattice parameter, which is this value, which is 3.345. And we were looking, if it was simple cubic, for 2.0269. So basically, since the only element that is simple cubic is polonium, its lattice parameter really doesn't match. We can safely say at this point that it's not polonium and it's not simple cubic if it is one of these elements. So we're going to instead shift our focus to BCC and look at only BCC elements and compare it to the 2.8665. So I'll kind of scan through here and you do the same and see if you can get anything that's close to 2.8665. So right off the bat, we see one here, but it's too high. Another BCC 6.0, so too high. Then this other one though, chromium, it's getting closer, 2.88, so pretty close. Another one, europium, but 4.6, too high. BCC, 2.8665. So that sure looks like what we have. And that's an exact match of what we have. In real life, you won't always have an exact match like that. But as you might have been able to tell, I made this pattern based on this lattice parameter. So if we look over, this is BCC. We know it's the right lattice parameter. This is alpha. This is iron, and it's alpha, which is the room temperature phase of iron, which is ferrite in some case, called ferrite. And so that would indicate that our material is alpha iron, which is also ferrite, and that's kind of our best match. If you keep looking, like I kind of mentioned, chromium fit pretty well, And the other iron, which is 2.9232, is also a pretty close match, but that's the best one, right? It's an exact match in this case. So you'll often find things that are relatively close. So you might have multiple close matches, and you want to just determine, or you want to look at which one is the closest in this case. So that's kind of just going through an example of how we could index a pattern with this simple method, and then if it's an element, use this table to cross-reference those values to see how close we are.